relax and ready anytime, Tristan. Anytime. You're good.
All right. Well, thanks everybody for showing up and showing up early by 5 minutes for the seminar today. It's my pleasure to introduce Juliet Pilewskie, who's worked with me for about 6 years now. Juliet joined my group in fall of 2017 after doing her bachelor's in physics at CU in Boulder. I had to think, twice about bringing on a flow, but it's worked out really well. I'm from CSU, we're big rivals, just so you know. But no, it worked out very well. She had done a lot of work on some really interesting problems related to remote sensing, but not in our field. She had studied surface deformations, excuse me, around Kilauea using synthetic aperture radar, as I understand, and also modeled the rings of interstellar dust around some celestial bodies, and wanted to apply those skills to understand climate modeling through observations. That came from the email that Juliet sent me about 6.5 years ago now when she was first looking for positions. So once I got her here, we started looking right away at the characteristics of deep convective clouds, and in particular, we wanted to focus on using new observations that actually get at their energetic and radiative impacts on the climate. So unlike a lot of research that focuses mostly on precipitation, Juliet's work has really focused on what the cloud fields look like in association with convection. In 2020, she was awarded a NASA Finest, and you can see that that's supported most of her research that she's going to present today. And then I could go on and on about the many things that Juliet's done while she's been here in Madison. But I do want to highlight one, I think, visit that really shaped her research and what she's going to talk about today. And that is she spent, it was either 6 or 7 weeks in France, working with folks at Météo France in Toulouse. And then at a workshop that we held just south of Paris, she met a lot of new people, developed a lot of new collaborations, and her research really just, I think, took off from that experience. And so that was about 1.5 years ago, and today she's going to share with you, I think, just a little bit of the work and some of the new directions that she's been spinning off from her research from those collaborations. So go ahead, Juliet.
I think I turned it off. Oh,
Just
there
hold,
we go.
Yeah.
Can everyone hear me? No? Yes? Is the mic working? Okay, great. Thank you so much. Well, thank you for that very kind introduction, Tristan, and thank you all so much for coming today for me to present on some of my PhD research that I've been working on. As Tristan mentioned, I have largely been studying deep convective cloud properties and their energetic contributions for kind of under the umbrella of wanting to reduce uncertainties in climate models. And so why do we care about the energetic impact of deep convective systems? Well, there are these convective updrafts within deep convective systems that vertically transport energy and mass into the upper troposphere. And then you also have this anvil cloud that develops, and they have a large radiative impact at the top of atmosphere. Clouds emit long wave radiation, and they reflect short wave. So atmospheric deep convection largely is integral to balancing Earth's radiative energy budget at the top of atmosphere. So we know that in the tropics there is an energy surplus, and that is due to the Earth receiving the most direct incoming sunlight or solar radiation compared to at higher latitudes on the globe. However, the outgoing terrestrial radiation, so the outgoing long-wave radiation, does not cancel out the absorbed solar energy at the tropics. And so there's a surplus at the tropics, but then a deficit at higher latitudes. And so energy must be moved to higher latitudes in order to maintain a balance. And how this is largely done is through the vertical transport of boundary layer surface or boundary layer air to the upper troposphere in primarily convective regions by the equator. And so in 1958, Herbert Real and Joanne Malkus, or Simpson, deduced that this region near the equator is a heat source, and you have these updrafts or hot towers that reach the tropopods that vertically transport this energy and mass. And that energy not only balances the radiative cooling in the clear sky areas, but then it also supplies energy for polar transports. So in addition to that upper tropospheric energy that's transported, we have the cloud radiative, or the radiative effects from the clouds themselves that contribute to balancing the energy budget at the top of the atmosphere. So I'll just go a little bit into the top of atmosphere cloud radiative effects in the tropics. So a cloud radiative effect is essentially the cloud contribution to the energy budget. You have the cloudy region, fluxes in the cloudy region minus the clear sky fluxes. And the net cloud radiative effect is equal to the contribution, the addition between the long wave component and the short wave component, where the long wave component is primarily you reduce, or the long wave becomes more positive as cloud height increases, and so that what that means is the clouds are they reduce the amount of outgoing long wave radiation because they absorb that energy, and then they also emit at lower temperatures. And so they contribute to warming. However, their short wave, depending upon their thickness, the cloud thickness, they actually, or the clouds actually become, they contribute to a cooling. And so in the tropics, you see an enhanced long wave cloud radiative effect and also an enhanced short wave. And so that contributes to an almost a balance, nearly an equal and opposite long wave and short wave cloud radiative effects. So in 2017, this paper by Hartman and Berry made this connection that, okay, there's a balance at the top of atmosphere within the tropics, or a near cancellation between the long wave and the short wave within the tropics. And it could be a coincidence that that's the case because, you know, you have the radiative effects are changing over the full life cycle of convective systems. However, he argues that there could potentially be a feedback associated with maintaining this balance. So what that means is a feedback due to climate change. And so there's been a lot of work looking into projected changes in atmospheric deep convection with climate change. People are thinking that within the tropics here, the region where convection is confined is going to be increasingly narrow in size, as well as the convection within this region is going to intensify, so it's going to get higher into the atmosphere, and precipitation might increase, and the anvil cloud will shrink, and so that has a lot of potential impacts for the amount of energy that is distributed within the upper troposphere and possibly to higher latitudes. So, however, there are a lot of uncertainties with these potential changes in cloud properties and how that might influence the energy budget at the top of the atmosphere. This figure here is the change in the energy budget as a function, or per degree surface warming, as a function of the changes in cloud properties. And I just want to direct your attention to this red box of the equatorial region, and notice that the orange line is, it is talking about the amount of cloud associated with the tropical clouds. And so it's a tropical high cloud amount. And then also the thickness of the cloud, the opacity that largely impacts the shortwave. There's low confidence in how these might change with climate change in models. And so before we can make an assessment of how the radiative energy at the top of atmosphere, radiative energy might change with climate change, we first have to get these radiative effects. We first have to quantify them with respect to all these different cloud properties. So the vertical intensity and how that relates to the cloud thickness, cloud top height, and such. And we have to do this on a cloud scale just because these systems are so complex and they do vary. And it's not enough to be doing averages over 100-kilometer domains, which has been done in the past. So we can use an A-train perspective of these cloud effects and their radiative effects. So A-train is a constellation of low Earth orbiting satellites that make observations twice daily, 1:30 a.m. and p.m. local solar time, and it has nearly global coverage. So the advantages of using an A-train satellite, of these observations, is that we have the CloudSat cloud profiling radar, and it is sensitive to cloud droplets. But then we also can combine these observations from the Calypso Calliope LiDAR that has even finer sensitivity to thin anvil cloud that has important radiative contributions. And then these measurements, in combination with some data from MODIS on board Aqua, are used to create go through radiative transfer model to then supply the 2B FluxR LiDAR product for the cloud radiative effects. So the focus of this presentation is to, we'll first introduce a convective object database using the satellite observations that documents convective cores, vertical intensity, anvil horizontal and vertical structure, primarily radiative effects in thermodynamic and dynamic environment. Don't have time to go into the precipitation. So this first analysis is largely inspired by Ed Zipser's work in using TRIM data to characterize deep convection on a tropics-wide basis. And so I'm just going to be presenting one slide highlight on this work, but I aim to answer the question on a global scale, where does atmospheric deep convection occur? And then the second analysis I'll be presenting is motivated by this work by Joanne Simpson and Herbert Reel in looking at, do hot towers, or these most intense deep convective cores that reach the upper troposphere, do they contribute the most mass in the upper troposphere relative to all the other deep convective cores? And then how many hot towers occur at any given time? And then finally, I will be looking at how do convective cloud thickness and radiative effects vary with increased vertical intensity. So extending outward to understand more of the cloud, connecting it to the anvil contributions, the radiative, anvil contributions. Okay, so we'll go into this A-train database, the convective object database. So what a convective object is just a cloud object, cloud system. Think about anything from an isolated deep convective system to something on a synoptic scale. So what we do firstly is we identify deep convective cores along a cloud set overpass. So this figure on the left here is a cross-section of a radar reflectivity profile from a cloud set with the height on the y-axis and the latitude on the x-axis, and it's colored by the radar reflectivity. And this blue line here designates a convective region, and the green line here designates the stratiform region. So the thing with the cloud profiling radar is that it is highly sensitive to precipitation. So it actually attenuates when the radar signal encounters precipitation. That means, if you can see the blue, on the figure on the right shows the height as a function of the radar reflectivity, and at about 10 kilometers, the reflectivity starts decreasing. And to contrast that with the stratiform region, which is in green here, you see that the decrease occurs at around the freezing level, which is what we are familiar with stratiform rain, that it's at the bright band or the melting layer where you have most amount of the rain occurring, whereas in the convective region it's higher in the atmosphere. And then I also just wanted to point out that you can notice that attenuation in the radar reflectivity profile, whereas with the trim reflectivity profile, which is plotted down here, it is able to detect the precipitation, and so you see these enhanced reflectivity values below this freezing level in the convective regime. So you know that there's a lot of rain that's extending to the surface. But it doesn't capture the cloud characteristics that the CloudSat does. So we require that the attenuating signal must be at least 1 kilometer above the freezing level for it to be determined a convective region. So then, once these convective regions are identified, we group them. If they're right next to each other or contiguous, we group them into deep convective cores. And then we use combined measurements from both the CPR as well as the Calypso LiDAR to identify the full convective object profile, so just collecting the contiguous cloudy pixels. And we do want to keep the Calypso only detected cloud because it's important for capturing the radiative effects again. So the figure on the right here shows, on the top is an example of a single core deep convective system. And so a single core is this this region of deep convection. You can tell by this enhanced reflectivity high up in the atmosphere. And then it has a little bit of a precipitating region denoted by the purple, and then non-raining in yellow. And the bottom plot shows an example of a multi-core system, so a system with several deep convective cores. And this is just to emphasize the difference in scalings of these convective objects. So on to our first analysis, or just a brief highlight. On a global scale, where does atmospheric deep convection occur? So we use these A-train convective objects over a 4-year time period on a nearly global coverage. And so this plot here on the right, the top plot, shows the number of convective objects divided by the number of CloudSat overpasses within each grid box. So we see that the higher the percentage, the more frequent convective objects are with respect to the CloudSat overpasses. So convection is most prevalent over tropical land and ocean at both times of day. However, we can, well, not however, but we can make use of the twice daily sampling of deep convection during this 4-year time period by taking a look at the difference between the daytime frequency of convection and the nighttime frequency of convection, which is shown by the plot at the bottom. And we do see that there are differences and where convection peaks. So convection occurs more frequently during the early afternoon than late at night over land, which I've shown by the red boxes. However, over the ocean, there is a slight tendency for convection to occur at the early hours of the morning. And just from previous work, we see that convection typically peaks in the early morning over the ocean. And when I say convection peaks, it means that convection is, or these deep convective systems are most frequent. So then on to the next analysis. Do hot towers contribute the most mass in the upper troposphere? And then providing an estimate for the number of hot towers. In the data for this analysis, we use the convective cores from this database. And I also, in addition to this 2B geoprobe that provides the radar reflectivity structures, we use the ECMWF-AUX data product to provide vertical temperature profiles that are used for identifying the hot towers. And then to characterize the high cloud cover, we make use of the series EBAF, monthly mean, top of atmosphere, all sky, long wave radiative fluxes. And just to characterize the climatological precipitation, we use iMerge monthly mean surface rain rates. And all data is during an 8-year time period, just to try to increase the number of samples that we get of hot towers and cores. So this analysis is primarily, it's concentrated in this region known as the equatorial trough zone, which is a region associated with poleward lateral transport. It was first defined in the Reel and Malkus paper in 1958, but we've since updated this, this paper by Stevens and co-authors have updated it to be over this region defined by the tropical trough zone, and that was updated using new series top of atmospheric radiative fluxes. And so this region is between 13 degrees south to 19 degrees north. We also ensure that deep convective cores have a cloud top height above 8 kilometers. And then to identify or to distinguish hot towers from the full span of deep convective cores, the deep cores that are hot towers must overshoot with the environmental tropopause, and so we have two definitions of the environmental tropopause. The cold point tropopause, which is the height of minimum atmospheric temperature, and then the lapse rate tropopause, the height at which environmental lapse rate is less than 2 Kelvin per kilometer. So it must overshoot both of those tropopause definitions. So the figure on the right, the bottom, shows this, again, the radar reflectivity profile of a full convective object, and all of the black dots correspond to regions of deep convective cores. And then I've shaded the regions that are considered hot towers with the blue. And so there's several convective cores within this convective object, but then there's only 2 hot towers that are in this system. And we see that the hot tower is slightly offset from this kind of bump in the radar reflectivity structure, and that is considered an overshooting top. So it could be that the updraft is slightly tilted, and so you're getting this overshooting top right here. So this plot here shows the number of all deep convective cores within each 8x4 degree grid box. So it's just adding up all the cores over this 8-year time period. And we see that the cores are primarily concentrated over what this region in the near the equator, consider the ITCZ, the Intertropical Convergence Zone. And then we also have a large amount in the over the maritime continent and into the SPCZ. And then over continental land as well, the Amazon and the Congo Basin. And just to compare that to the high cloud cover by the long wave radiative fluxes, we see that there's a reduced outgoing, or the OLR is very low over the same regions that there are a large number of cores. So that just means that these deep convective systems are producing a lot of cloud that reduces the outgoing long wave radiation. And then this figure on the right here shows the monthly mean surface rain rates. So these systems are also correspond to a lot of precipitation. But then if we take a look at the fraction of hot towers compared to all deep cores, we see that hot towers are most prevalent along the kind of on the fringes or the outskirts of where the high cloud cover and rain rates are. And and also I wanted to point out, although that's the case, you do still primarily see a hot spot of convection, or these hot towers, these most highest the convective cores, concentrated over the maritime continent and West Pacific, and we know that especially over the West Pacific there are these warm sea surface temperatures, and so it makes sense that they're thermally driven. There's compared to over the East Pacific, that these systems are a lot more dynamically driven, so the convection is more often occurs in the thermally driven environment than dynamically driven. So now let's go on to defining the convective core vertical intensity by its relative center of gravity. In observations, it is really hard to capture the intensity of deep convective systems because typically people characterize them based on their vertical velocity, and we do not have measurements of the vertical velocity on a global scale. So we can make indirect or somewhat indirect measurements by capturing the center of mass of the largest hydrometeors that are being wafted into the atmosphere within these deep convective core regions. And so the center of gravity of a convective core is the average height of the convective core weighted by its reflectivity, since the radar reflectivity is proportional to the cloud particle to the 6th power. And then we subtract the center of gravity of these cores by the height of the freezing level, just to really capture how much higher their extent in the atmosphere. So this figure here shows a composite of single core only convective objects of their radar reflectivity profiles over the tropical ocean in 2010. And the figure on the left is sorted by the lowest possible relative center of gravity, so these weak convective cores, and then we have the highest relative center of gravity convective objects on the right. And so we see that the radar reflectivity signatures are not only higher in the atmosphere, but they're actually also wider too. So the higher the convective core RCOG, the deeper the convective system is in the atmosphere. So what does this look like on a tropical scale? Well, we see that the RCOG for hot towers only are much higher in magnitude than the RCOG for all deep convective cores. In fact, the hot tower RCOG is about 132% higher than that of all cores. And they're predominantly the highest over over land. So then we can look at the hot tower diameters. So that's just the width of the hot tower or convective core along the cloud-set overpass. And again, the hot tower diameters are much larger than the diameters of all cores, about 150% larger. And there is some distinction between the hot tower diameters. They're slightly higher over land than over the ocean. And this is consistent with some previous work that a colleague, Hani Takahashi, has also been looking at. So then we can define a proxy for kind of the vertical mass contribution within the upper troposphere, and as the number of pores, so the frequency, how frequent they are, times the vertical intensity proxies, the RCOG, times the pore diameter. And for the hot towers only, which is the figure on the top, we see that the this vertical mass transport proxy is highest over land, and also kind of in the regions, predominantly in the regions where hot towers are most prevalent. And we see that's the same thing for the distribution for all deep convective cores. And so, because hot towers are so infrequent, the total mass contribution from hot towers is much less than that of all deep convective cores. And so I think I want to bring up the point that the Reel and Malkus paper, they argued that it was these hot towers that are contributing all the energy to balance the Earth for poleward transport, and that they are actually rather infrequent. There's been a lot of updated work on this previously, suggesting that hot towers, it might not be the case that they're contributing all of the energy for poleward atmospheric transport, that there are potential, that you have to consider the latent heating contribution from precipitation, as well as the radiative effects from cloud. Nevertheless, I provided an estimate for the hot towers at any given time as 1,500 to 3,200, and this is actually somewhat consistent with this Reel and Simpson estimate of 1,600 to 2,400 hot towers at any given time. I don't have time to go into the full methodology of that estimate, but if you're interested, feel free to ask at the end. But I did I supplemented the A-train data with geostationary observations to provide a more spatial temporal perspective on these deep convective cores. So finally, we'll look into how do convective cloud thickness and radiative effects vary with increased vertical intensity. And so we'll use the A-train convective objects, the RCOG, the vertical intensity, proxy, cloud optical depths, and cloud radiative effects over a nearly 10-year time period over the tropical ocean. So just as a refresher, there are predictions being made for the cloud radiative effects by a changing convective structure within the tropics. However, there's large uncertainty associated with these projected changes, and so we have to first understand the relationships. We first have to characterize them in our current climate and connect them to these cloud properties. So the top of atmosphere total net cloud radiative effect from convective objects is, they predominantly contribute a net cooling. And we can see this because if you take a look at the total cloud cloud radiative effect in the long wave, which is the top figure on the left, and then the short wave on the right-hand side. When you combine them, you see that the short wave component outweighs the long wave. However, there is large variability in the net cloud radiative effects over the full ocean, and so that suggests that there are the cloud properties of all these different convective objects are very very different. So this is a diagram showing the varied types of tropical oceanic convective objects. This first column here shows what we define as the congestus mode. So we require that it has a cloud top height less than 8 kilometers. And then a deep convective mode, which is the cloud top height greater than 8 kilometers, which are these next two columns. We define single cell and multi-cell. So single cell is the top row, multi-cell is the bottom, and a single cell system is a convective object with one precipitating core. So it can have, one precipitating region. It can have multiple deep convective cores, but it must be connected with by precipitation. And then we have the ice-only, or under the deep convection mode, there's this ice-only category, which we define as the system predominantly having just the high level or ice-only or supercooled liquid water within the anvil. But then there's an underlying liquid mode under deep convection that can have low-level cloud, and it's important to make the distinction between these two because the low-level cloud also has their own radiative effect. Yes?
Juliet,
Yeah.
is this partly a function, I'm looking at the top left, the
Yeah.
ice-only single cell and then the multi-cell underlying liquid.
Yeah.
One could imagine that as the life cycle of the bottom right continues, maybe only the strongest of those 4 cells last, and you might later on observe it as an ice-only single cell. Is that possible?
Yes.
But it's just small probability.
Yeah. No.
Or small collection of the total. Is that right?
Yeah. Well, that's a really good question because, yeah, we are not. So are you saying that we could be capturing the same system?
I'm wondering if
potentially
you're just observing
yeah.
it at different times in a life cycle. So this
Yeah.
doesn't have a life cycle umbrella on top of it. It just has an instantaneous observation.
Yeah, it is
right?
only instantaneous. We do have plans to look more into
Okay.
the life cycle. It's hard to say because the CloudSat observations are quite limited.
Right.
I wouldn't say that it is capturing the same system unless it's like a larger scale. Like,
Yeah. But maybe you're capturing a similar system at another time in a similar life cycle.
Yeah.
Okay. Thanks.
Yeah. Thank you for that question. And if anyone else has any questions, please do not hesitate. So we'll be focusing primarily or only on these deep convective systems. So, as I mentioned, the cloud properties largely influence the radiative effect at the top of atmosphere. This figure here is the cloud radiative effect on the y-axis and the cloud optical depth on the x-axis. And so you can think of the cloud optical depth as the thickness of a cloud. And we see that both the long wave cloud radiative effect in red and the short wave vary as a function of the cloud optical depth. The long wave it varies with the cloud optical depth because the thinner the cloud is, so the lower optical depth it is, the more outgoing long wave radiation can transmit through the cloud. It has lower emissivity. But as the thickness of the cloud increases, the the long wave cloud radiative effect kind of dampens, it plateaus. Meanwhile, short wave, this plot really should be going on for much larger optical depths because it will just continue to go become more and more enhanced. So it increasingly reflects and scatters radiation, essentially becomes opaque. So we define two regimes of clouds having, so thin cloud regime, so a cloud optical depth less than 1, and then thick cloud has a cloud optical depth greater than 3. So just to kind of point that out a little bit more, here's the radar reflectivity profile of a convective object, single core system. And then the middle plot shows the long wave cloud radiative effect in red, short wave in blue, and net in green. And then the bottom panel shows ice water path in blue and the cloud optical depth in red. And so perhaps it's a little bit challenging for you to see, but there's a dashed line on the bottom panel that corresponds to a cloud optical depth greater, or of 3. So we see that for a cloud optical depth less than 3, we have primarily the net cloud radiative effect is positive because the long wave is high, primarily due to the high cloud tops. But there's really no short wave effect, and we see that the long wave also it's more enhanced than the short wave for below a cloud optical depth less than 3. But then as soon as the cloud optical depth jumps up higher than 3, we see that the short wave quickly takes over and that the cloud contributes a net cooling. So this figure here is a density plot of, so it's all of the convective objects, these deep convective objects, as a function of the fraction of thin cloud that it contains versus the fraction of thick cloud that it contains. And this is kind of just, the dashed line shows the 1-to-1 line. And each contour represents 10% of the population. And it's sorted by all convection in black, single cell convection in blue, and multi-cell in green. And we see that these convective objects tend to have more thick cloud than thin cloud, as we can tell by just the distribution of these. Yeah. Okay.
Is it the same?
Yeah. Sorry.
What about the covariance of thin cloud and thick cloud? It's saying they are. Oh, I see. It's percentages. Okay.
Yes. Yeah. Okay. So, what is the role of cloud thickness fractions in modulating these cloud radiative effects? Well, so this figure here is also a density plot, but now it has the long wave cloud radiative effect at the top of atmosphere on the y-axis, and the short wave on the x-axis. And we can define two regimes by their cloud thickness fractions. Well, generally, as I mentioned earlier, these convective objects have a higher short wave impact than their long wave. And so what we define as the thick cloud regime by this white circle here, it's the fraction of the cloud optical depth, or so the thin cloud divided by the thick cloud, the ratio. And so it is, this thin to thick cloud ratio is less than 1. Sorry, in the histograms here are colored by that thin to thick cloud ratio. So this thick cloud regime has both the highest long wave and the short wave cloud radiative effects magnitudes, and they primarily contribute to cooling. Meanwhile, we define a thin cloud regime as the fraction of thin cloud divided by thick cloud, and that's greater than 1. And so that's shown by this red circle here. And we have the lowest long wave and short wave magnitudes. And these systems can often contribute to warming. But we see that there is generally even a large spread in all of the cloud radiative effects. And so we know that we can't just look at the cloud thickness, we also have to take a look at how the cloud top heights influence the cloud radiative effects. So this figure is showing the cloud top height on the y-axis and the thin to thick cloud ratio on the x-axis. They're kind of logarithmic scaling on the x-axis. And for the long wave cloud radiative effect, we see that it is most enhanced for the highest and thickest clouds. Similarly, for the short wave, we see that, the short wave is most enhanced for the thickest clouds, and it strongly decreases as the fraction of convective objects get thinner. And then the net cloud radiative effect, we see that clouds contribute the most net cooling if they have the lowest cloud top heights and also are the thickest. Meanwhile, they contribute the most warming if they are the highest and they are the thinnest. So that is something that is learned in kind of fundamental irradiation class. But now which radiative effect is greater as convective intensity increases? So we can bring back the same density plot from a couple slides ago with the long wave top of atmosphere cloud radiative effect on the y-axis and the short wave on the x-axis. But now we sort the convective object populations by their RCOG value, that proxy for vertical intensity. So this leftmost plot is the weakest intensity populations, and the rightmost is the strongest. And again, these histograms are colored by the thin to thick cloud fraction. So you can see that there's a general change in the distribution of these convective objects, as they're in the most intense population is moving more towards this black dashed line, so they have a tendency perhaps to increasingly contribute a warming. And just to kind of further show that, we can take that density plot of the most intense convective systems on the left-hand side and the weakest systems, to do the difference between those populations. And that is what, these colors are not showing up great. Sorry about that, but these colors show the difference between those populations. The purple bullseye is the weakest, green is the strongest. And it's colored by the normalized counts for these two populations. So the reason why there is this distinction, we can again look back at how do the cloud thickness ratios and the cloud top heights change as the intensity of systems increase. So the figure on the left shows for both single cell and multi-cell, the general spread, overall spread is for systems to slightly increase in, the thin cloud fraction slightly increases. So you have more thin cloud with respect to thick cloud. However, it is a little bit hard to say that for certainty, just because there is such a large spread in the cloud thickness ratios for the most intense systems. But then you see this noticeable increase in cloud top height as the intensity increases. So because of that cloud top height increase, the long wave cloud radiative effect is enhanced. And so that is why the populations, for the most intense populations, move up, their long wave cloud radiative effect increases. And so, yeah, the long wave outweighs the short wave, which shifts the full distribution towards weakened cooling and slight warming. However, for the thick cloud regime, it looks like the short wave cloud radiative effect slightly enhances, because the thick cloud increases at the expense of thin cloud. However, it's a lot more noticeable that in the thin cloud regime, you have the thin cloud increase at the expense of thick cloud. So you have a reduction in the short wave cloud radiative effect. And just to reiterate, it's that large spread in the thin to thick cloud fractions that contribute to this much larger spread in the radiative effect for the most intense systems. So to summarize, we saw that in the first analysis that A-Train can capture signatures of deep convection on a nearly global scale that are consistent with previous work that's been done in this. And then for this hot tower analysis, the hot towers are both more intense and larger than cores, but they're much more infrequent. And we estimate that there are about 1,500 to 3,000 or 3,200 cores at any given time. And then finally, for this last analysis, we saw that deep convection primarily cools, but the cooling weakens as convective intensity increases. And because of that large variability in cloud thickness for the most intense systems, this causes a large spread in their radiative response. But more work needs to be done to look at how these cloud properties and their radiative effects vary as a function of their large-scale dynamic and thermodynamic environment, and also, as John mentioned, being able to capture the convective life cycle and how that influences the cloud properties and radiative effects. So, because deep convection is primarily constrained to these regions of large-scale ascent, which we define as the 500 hectopascal vertical motion using narrative reanalyses. And also, it's primarily confined to warmer sea surface temperatures. We can take a look at, or we can sort these convective cloud types based on their large-scale thermodynamic environments. And so, kind of across the board, so this is a heat map showing the change in the net cloud radiative effect at the top of atmosphere as a function of the change in the increased intensity. So how does the net cloud radiative effect change when you go from, when you increase in the intensity of the system? And we see that, in the y-axis is showing the omega 500 regime, going from descending the top here to ascending the bottom, and then going from cold sea surface temperatures to warmer sea surface temperatures. And so the net cloud radiative effect increases, so it gets enhanced as intensity increases, and it could be that it's due to the increase in cloud top height, but there's some more work in capturing the statistics, primarily because the changes in cloud top height with the vertical intensity are not statistically significant, nor is the cloud thickness for some of these regimes. So yeah, just more work needs to be done in that. And then another aspect that we wanted to capture is their changes in the cloud radiative effects over the life cycle of deep convection. And so this paper by Yoon and House, they postulated that anvil extent, so the cloud extent from the deep convective core, is a signature of the life stage of convection. So you can think of a developing system as just being primarily composed of thick cloud without much anvil that is detraining from the core. Whereas a mature system, it's mostly dissipated, so you do not have that extensive core, and you just have a lot of this high thin cloud in the atmosphere. And so for a given intensity population, the life cycle of a convective system can be traced. And so I have this, the long wave versus short wave cloud radiative effect density population. And the histogram now is colored by the convective object length. And then, so we see that perhaps at the initiating stage, you'll have enhanced short wave contribution, but the cloud top height extent is not very high yet. So the long wave component is not high. Then more in a mature stage where the radiative effects are nearly neutral. And then the dissipating stage 3 here could be where the clouds are mostly high, but they're thin. And so they primarily contribute to warming. But it perhaps on an even more robust understanding of the convective life cycle, we can supplement the A-train observations with geostationary satellite data to capture more spatial and temporal coverage of these systems. And so this is some of the work that I had been working on last summer in France with a group in Toulouse, in looking at some geostationary data that is able to track mesoscale convective systems in both space and time. And so each mesoscale, or MCS, mesoscale convective system, is colored. And we see that there are so many, so it's just quite impressive to try to be able to characterize all of the energetic contributions of each of these. And so I will skip that, just saying that there's a lot of applications of this convective object database, particularly for future satellite missions. And the convective object database will be made publicly available in the CloudSat Data Processing Center. So sorry I had to rush because I just noticed the time, I apologize, but I just wanted to end and give a big thank you. Thank you so much, Tristan, for just being an incredible advisor, seeing me at my best and my worst, crying in France after a conference, yeah. My Ph.D. committee, Andy Heidinger, Stephanie Henderson, Angela Rao, Sam Steckman, thank you so much for all of the contributions and your suggestions that you've made for me. The whole LECBA group in general, I really enjoyed just working with all of you and getting to hear all of your thoughts. And all of your research too. It's really quite impressive how vast the research spans in our group. Dave Henderson, he sat down with me after my master's work, and I wanted to, Tristan and I had talked about improving this methodology, and he suggested perhaps maybe looking at these systems on a convective object scale instead of just trying to do a bunch of statistics and averaging over much larger domains. And so I greatly appreciate all the time and effort that he's helped, he's helped me a lot. And then in terms of my research collaborators, Graham Stevens, Tristan's former advisor, has been really influential in helping me understand some of these hot towers and pointing me to getting at this, thinking more about these types of thoughts about the vertical mass transport. Hani Takahashi has been a great collaborator, and I'm excited to be working with her to co-organize a workshop for being able to track these MCSs. Dominique Bugnol was the one who hosted me in France last summer, and I just really enjoyed working with her. It was really incredible. This water cycle workshop, I worked with Chloe Redis, Pierre Costetter, Thomas Fiolo, Helen Brunier, and Johnny Lowe, and that was great too. Kyle, thank you so much for letting me kind of mentor, and it was incredible to see all the work that you did with the TC, so that was great, and I'm excited to see where you're going with your PhD. I've been really enjoyed working with Ben Rodenkirch and also Angela for studying convection over the Atlantic Ocean. Anita Rapp and Savannah Elkins down in Texas have been really doing a lot of great work as well. And then Bowen Pan, Aurea Drager, and Sue Vandenheber for their work in studying some of the environmental properties of these deep convective systems. Larissa and Angel, thank you so much for just teaching me so much about tropical convection, and I'm excited to continue getting to just understand it more. And Ankur and John, I feel like you've given me a lot of sage advice over the years, so thank you for that. Pete, thank you so much for all your technical help. It's been great. Christy, Carolyn, Dee, the administrative team, thank you so much. All the AOS grad students. And then lastly, well, not lastly, but friends through AOS, SSCC, and SIMS. We've got Julia, Bailey, Maria, James, Victor, Susie, Zoe, Vidget, Miguel, John, Young, Tim Schmidt, Srinath Pirliri, Andrew Zambo, and Ann Sled. Most of you guys are online, but yeah, thank you so much. All my friends that came. And lastly, but not least, my family. Yeah, it has been amazing having you in town and providing a nice distraction. This past weekend was a little bit challenging. So I really appreciated just all your support there. So thank you. And sorry about that.
Very nice, Juliet. I think you can go ahead and call on people for questions if you want to. We usually start the question and answer with earlier career or students if they have any questions.
There's a grad question online
Okay.
too, from Posh. Says, awesome talk, Juliet. How did you go about deducing the constraints you used to identify your cores and hot towers? For example, CTH greater than 8 kilometers, were they empirically derived?
Yeah, so that was mostly actually was empirically derived. I was looking at the radiative effects of these deep convective systems and noticing that there was no change, that the clouds below 8 kilometers were just constantly contributing a cooling regardless of their thickness properties, and that is due to the scattering associated with ice versus liquid, and so yeah, it was more empirically, yeah, so determined that the cloud top height above 8 kilometers were more deep convective, yeah. Yes, Hamish.
That's cool. You gave us like 2 potential possibilities for intense convection intensifiers depending upon cloud thickness. Do we have like an inclination in the future which direction things might go in if we get into steam increases? Will we expect thicker clouds and so we get a more warm and cooling or thinner clouds?
Yeah, that's a good question. So there's a popular, the most prominent theory is that the anvil cloud, or so the tropical anvil cloud will reduce, so clouds will thicken. It's hard to say what will happen within the convective system because that very much depends. You know, the clouds will get higher in the atmosphere, and so that would enhance their long wave component, but then if they're also getting thicker, then that could enhance the short wave. So it's challenging to say what could be the case, but if the high cloud amount is decreasing, then you're having, and also the surrounding regions around around the deep convective systems are expanding and drying, and so that is enhancing the outgoing long wave radiation. And so what's really important is to, in future also, to characterize the radiative effects in the clear sky regions. Yeah. Yes.
If I remember correctly, sorry, with the Real and Malkus work, they were kind of seeing like the hot towers as like those regions where your convective core is not like highly affected by entrainment. Did you consider that as well, or is it just more of like on your perspective on hot towers?
Yeah.
Or entrainment can or not play a more important role?
That's a really good question, because we did not look at all into entrainment effects, because the Real and Malkus hypothesis, they assumed that these hot towers did not bring in the surrounding like environmental air, so they are primarily what's known as undilute hot towers. But there's been a lot of work since, including work by Ed Zipser using TRIM, and also some field campaign data that showed that there's no such thing really as a convective core that doesn't entrain air, but that it could still be the case that hot towers, or these really deep cores that are reaching the upper troposphere, can contribute to the energy within the upper troposphere due to more thermodynamic, like freezing and latent heat release, and so that would supply the energy in the upper troposphere. So we didn't look at all into entrainment, so this is just providing kind of a perspective on cores reaching the tropopause.
Then as a follow-up, if
Yeah.
that's okay. Then I find it curious that your numbers of like estimated hot towers matched with what they have. So I'm curious, could you go a little bit into how you determined that?
Yeah, absolutely.
Like if you knew that.
Yeah. So, sorry, I'll just. Sorry, this slide is going to be quite busy, but I'll step through it. So this PDF shows the counts of hot towers as a function of their 11 micron brightness temperatures. So we matched all the hot towers to the geostationary brightness temperatures, and from Aqua Monas, and we saw that the brightness temperatures are primarily 200 Kelvin and below. This is also just another kind of more 2D histogram showing the cloud top height of these hot towers as a function of their brightness temperatures. And then we used that 11 micron brightness temperature, so 200 Kelvin or less. We calculated the surface area of this tropical trough zone with that contained 200 Kelvin or less brightness temperatures. And so, the fraction of the brightness temperatures less than 200 Kelvin over this region calculate the surface area of the TTZ covered by hot towers. So our new definition of hot towers was based on this brightness temperature, and that just kind of shows the fraction of the TTZ less than 200 Kelvin, the diurnal cycle of that at each hour, which is plotted on the x-axis. And then we just calculated the surface area of a single hot tower by taking the width of the hot tower as the diameter, and then we divided the surface area of the full TTZ less than 200 Kelvin divided by the surface area of a single hot tower, to then get this estimate. And so then that sampling, that range, the 1500 to 3200, is the range over the course of a day. And we also kind of looked at that over different regions within the TTZ. Yeah, for sure, yes.
Juliet, really interesting stuff. Could you use your results to construct a conceptual model of a convective event in the tropics that has a net zero radiative impact? And then use observations to compare how things are straying from that conceptual idea.
Yeah, definitely. And so
you could integrate life cycle questions into that.
Yeah.
That's what I'm thinking, because one of your graphs showed that. So I meant to say that. You can conceptualize a life cycle that leaves no radiative impact at all.
Right.
And how do the actual systems behave relative to that conceptual model?
Yeah, exactly. No, that's I think so, because Dennis Hartman, that's kind of one of the ideas that he has for why convective systems contribute a balancing. Their long wave and short wave cloud radiative effects contribute near neutral impact, and it would not just be over the full life cycle, but it would also be they have to have the right cloud properties that they average. It would be over time too. Sorry,
But you have horizontal radar satellite depictions that could tell you about spacing between types of entities and so on, so you know how much clearing there is, as you mentioned before.
Yeah.
And so dividing that area by 4 or something, around a cell, you could kind of make some approximation about what would be the net radiative zero event.
Yeah.
What would it look like in its life cycle? It seems to me, I don't know, I'm clearly ignorant on this stuff, but it's interesting.
Yeah, for sure. Yeah, I kind of started looking into that a little bit of potential, like the short wave and the long wave contributions. This is actually work done by Bob Howes in 1981. So these ideas that they kind of perhaps balance out over the full life cycle, or have been considered for a while. Yes, Larissa.
Interesting data set. And
Yeah.
Nice talk.
Thank you.
Nice work.
Yeah, thank you so much.
I'm curious about your convective objects. You said have a negative net radiative effect.
Yes.
But the Hartman picture is a neutral net radiative effect. Why the discrepancy there?
So I think it could be because the convective object database, if we considered the kind of the dissipating or the decay stage of convection, as it may not have a deep convective core in the decay stage, and it's in that stage where
the objects had to have a deep convective core.
Yes, we require that the objects have to have a deep convective core, and in the decay they might not have that, and that's primarily where the warming occurs.
Thin cirrus.
Thin cirrus, stuff like that. Yeah, so it is definitely dependent upon how you define a full convective system. And the radiative effects of it. So it would be really cool in the future to try to capture more of the dissipating and decay stages. Rudra.
Hey Juliet.
Yes.
Great talk, very interesting and insightful as well. I'm wondering whether there is a role of wind shear or vertical profile of winds that affects your cloud thickness or cooling of cloud at any point in the tropics, and that would help you bifurcate some of the results as well, or just wondering.
Yeah, definitely. Actually, looking at vertical wind shear has been doing that a lot with Angela and Ben, in looking at how that impacts kind of the size of these systems, as well as the area of like stratiform precipitating versus non-precipitating areas. And I can't say much more on that because it's still ongoing work, but yeah, you're totally right. Shear would impact these systems, Yes.
I might have missed this earlier in the talk, but when you're, some of this later stuff that you're talking about, the energy balance, are you only looking at convective systems over the ocean, or is this all tropical convective systems?
Yeah, so we're just looking at convective systems over the ocean.
Okay.
because a lot of these climate theories are over ocean only, and land is really challenging to capture. Yeah.
Have you spent a lot of time looking like over the Amazon or that sort of thing?
A little bit, but it's not.
Oh.
Yeah, it would be really cool to see the land impacts.
Yeah, I was thinking just looking at it, I wonder if you could get a timeline of as the land's type changes because of deforestation, like if you can see differences in the convective systems in the region, that would be a really cool thing. I'm not
That
sure
would
how
be
long
really
your
cool.
time series is, but
Yeah, this is a 10-year time period, so I'm not sure, but that would be really interesting to look into. Yeah. Thanks.
I think maybe in the interest of time, thank you for all the questions. Thank you for the great talk. We'll congratulate Juliet one more time. And then what I would ask, I think, is for all of the committee members in about 5 more minutes to reconvene in this room, and we'll have just a few closed-door questions for Juliet.